Hello everyone, my name is Rohit Nayak. I'm a final year CS student at IIT Delhi. Today I'll be talking about hashing as part of my COQ course. I will start by presenting a problem and how hashing can dramatically improve its performance. Then I'll explore the different methods hashing can be implemented, and finally I'll also talk about how hashing has been used in other areas such as cryptography. Okay, let's say you have to maintain a record of all students enrolled in an institute, and you want to be able to perform operations that can manipulate this record. Now, each student has been given a unique ID for identification. Now, think of all the operations that you should be able to perform. You should be able to perform search, insertion, and deletion with high efficiency. The most simplistic and naive approach to this problem would be to store all the students in a linear array. In such an array, a lookup, basically a search, would take order n, insertion would take order 1, deletion would take order n. Insertion would take order 1 because you would simply have to you'd simply insert the new student at the end of the list. Deletion can take order n because the actual process of deleting would take order 1. However, you'd have to rearrange all the elements by shifting all the elements to the left or right, which can take order n. A slightly better approach would be to store all the students in a somewhat sorted manner. You can do it by implementing a binary search tree. In a binary search tree, these three operations, search, insertion, and deletion, can take order log n. Order log n is essentially the height of the tree. An even better approach would be to maintain a lookup table. Basically, the entry number of the student can be used as an index ID to directly index into the lookup table. Now, this can simplify our operations of search, deletion, and in search, deletion, and insertion dramatically. It can reduce them to order 1. But of course, our entry numbers would have to be integers, and there would be so much wastage of memory if we were to consider the entire length of the entry number as an array index. For example, if we take a current entry number to 2015 CS10229, there are 11 characters. Now each character can take an alphanumeric character. So a total of 36 power 11 students. Now obviously there are not those many students enrolled at IIT Delhi, and if we were to actually maintain an array of that huge size, there would be so much of wastage. Now, so the given entry number is such that the possible characters can be greatly reduced. For example, if there are no students that are enrolled before the year 2000, the first two digits can be omitted. The characters signifying the department are not do not have as many as 100 possibilities because there are just 10 to 15 departments in IIT. So basically, if we knew if we had a background knowledge of the entry number or of the student ID, we can greatly reduce the size of the array. So this is a rudimentary form of hashing. So basically, in hashing, what we are doing is we can take an ID, a given ID, and convert it into an integer, and use this integer to directly index into the array. Now, this concept becomes more useful if you have millions or billions of data items. For example, we should be able to convert a string of any length into a fixed finite length integer. And as we have seen, this enables us to quickly get access to the data that we are looking for by simply applying the conversion algorithm to attain an array index value directly instead of looking at through every index. So a hash function is a function which basically takes in a string value of any length and converts it into an integer of a fixed length. For example, here it can take keys which are basically the names of people, and we can apply a hash function on these names to give us a hash value from 0 to 15. Okay, so now so what are the desirable properties of a hash function? Okay, so you would be performing this you would be applying this hash function on basically every key value. So this hash function has to be extremely fast, and preferably it should take constant amount of time. It should be able to distribute the keys evenly in the hash table. Basically, you wouldn't want too many key values pointing to the same hash value. For example, in this case, John Smith and Sandra D, they both point to the same hash value, which is 2. This is an undesirable effect because it may cause collisions in our hash maps. Yeah, and basically we would strive to have unique hashes for every input key. For example, examples of how basic hash functions have been implemented are: example 1, you can basically sum up each of the characters and mod by the size of the hash table. This is very simple. It's very simple to compute. It can be computed very fast. However, this can give rise to multiple collisions because firstly, it gives no importance to the order of the array, order of the characters in the string, and there are many string instances that can give you the same hash value. For example, hash, mash, trash, and stash. They all give you the same hash value. Another example is to group parts of the key and apply some sort of an arithmetic operation on them. For example, you can apply. For example, if you were given a phone number, and if these are the respective country codes or area codes or local codes, you can group some parts of these keys, and you can apply some sort of an arithmetic operation between them. These arithmetic operations can be of any type: addition, subtraction, or XORs. Mid-square function. Mid-square function is basically you can take any integer, find the square of the integer, and take the middle. The square of 3121 is 9740641, and take the middle 3 digits, which is 406. Another example would be to iteratively multiply each character of the given string and add a constant term at each step. For example, 3128 upon applying this operation gives you 226. So, however, as you've seen, no matter how good your hashing function is, you will always encounter collisions. If you have a hash function which is as bad as the first one, as simple as the first one, you can get multiple collisions on the same key. So we basically need ways to handle these collisions. Two of the most common methods that have been used to handle collisions are chaining and open addressing. Now, chaining. In chaining, at each level, at each cell of the hash table, you're maintaining a linked list. So basically, if you have multiple key values that give you the same hash value, at that at the cell of that particular hash value, you maintain a key, you maintain a linked list, and you keep appending uh, all the colliding key values. For example, in the given slide, after you've inserted 750 and 76, let's say you encounter 85, and 85 has the same hash value as that of 50. Now, since you're maintaining a linked list at every cell, you can simply append 85 to the linked list present at 1. If you have 92, which again collides with 50, you can append it to the linked list that you're maintaining at 1. Similarly, for 73 and 101. Now, open addressing. Open addressing is a very different approach from chaining. In chaining, you're not trying to expand the actual hash table, but you're trying to expand at the level of each cell. However, in open addressing, you basically whenever there's a collision, you basically try to look ahead or probe through the array to see if there's an empty spot where you can directly put the incoming key value. So this basically requires that the size of the hash table is usually greater than the number of keys you have. Now, this active probing or looking for alternate solutions for a colliding key, you can use several strategies to find such an alternative location. Some of the most common strategies that have been used are linear probing, quadratic probing, and double hashing. Linear probing is the simplest of them all. As the name suggests, whenever you have a collision, you basically look ahead one cell at a time to find an empty spot. For example, once 776 and 50 have been inserted, and you have an incoming 85. Now, as you've seen from the previous slides, that 85 has the same hash value as 50, which is 1. So you basically look ahead and find that an empty spot exists at 2. So you basically insert 85 at 2. Now, so when you're trying to insert 92, even 92 has the same hash value as 50. So you look ahead. You look at 2, it's already occupied. You look at 3, you find it empty, and you insert it at 3. So on and so forth. Quadratic probing. So in quadratic probing, this action of look ahead is governed by I square in an ith iteration. Basically, you look at a hash value. Basically, let's say you're given x. You find the hash value of x. If the hash value of x is not occupied, you simply insert it with that value. If the hash of x is occupied, then we try hash of x plus plus 1 times 1, because since this is the first iteration. If even that is full, you try hash value plus 2 times 2. If even that is full, you try hash value plus 3 times 3, and so on and so forth. In double hashing, you maintain 2 hash functions, hash 1 and hash 2. So hash 1 is basically the default hash value that you use, hash function that you use. If by hash 1 you experience a collision, you try I times hash 2 in the ith iteration. So basically let hash x be the slot index computed using hash function. If hash x is full, we try hash x plus 1 times hash 2x. If even that is full, we try hash x plus 2 times hash 2x. If even that is full, hash x plus 3 times hash 2x, and so on. A note on deletion. Okay, whenever you're linear probing. Okay, for example, let's look at the given string of commands: insert 3, insert 10, insert 17, delete 10, and search for 17. Now 3 is inserted at the index value 3. 10, I'm sorry, and the hash function that you're using, let's say it's mod 7. 3 is inserted at the index value 3. 10 mod 7 is 10 mod 7 is 3, which is also inserted at index value 3. However, since 3 is already occupied, you'll be inserting it at the index value which comes after it and is free. Now insert 17. 17 mod 7 is again 3. You linear probe, you find that the fifth slot is empty, you insert it there. Now delete 10. So the deletion action also follows the same strategy. So deletion basically involves two things. You first look for the value, and then you delete the value. Then looking for the value follows the same strategy as insertion. 10 mod 7 is 3. Look, you go down to 3, and then from there on you try to compare if you found the given result. So 4, you delete 4, but however after you've deleted 4, you got to mark the cell so that the next search operations can skip the cell. So basically, after you've deleted 4, and if you try to search for 17, you come here, you see that the cell is empty, and you might be tempted into thinking that 17 was not found. However, since you've flagged the cell, you know that there are elements after this, and you go on to the next element after this, and you found 17. So basically, during the deletion operation such as del 10, we have to mark the cell as deleted, otherwise future searches might fail. Now I'll try to explain the difference between chaining and probing. Okay, in chaining, the entire table never fills up. Basically, at each cell, you're extending the table. In probing, however, the table can fill up. But however, there is better utilization of table space. In chaining, all the additional collisions are handled at the same cell by appending to the linked list that is present at the cell. In probing, the entire table can be filled up. Chaining is less sensitive to hash function and load factor. Load factor is basically defined by size of the table by the number of keys. It is less sensitive to hash function because even if there are collisions, even if there are too many collisions by a given hash function, they are handled well by appending to the linked list present at each cell. Probing, however, is limited by the table size, and care should be taken to avoid cluttering or high load factor. If the table size is too small, probing basically completely relies on the fact that you probe ahead and you look for an empty space where you to put the new coming value. So having a small table size, it can significantly worsen your performance. If the chain becomes too long, the search time can take order n in worst case. Basically, if there are too many collisions occurring with your given hash function, all your key values will be inserted at the same cell, and the length of the cell can go as high as n. Basically, all the elements can be inserted at the same cell, and any lookup can take as much as order n time. Chaining is basically used when it is not known how many or how frequently keys are going to be created or inserted. Probing, however, provides a better cache performance as everything is stored in simply one array. Applications of hashing in various areas. Now, hashing has been used in cryptography, and it has been used in designing caches, predicting data, Bloom filters, and geometric hashing. I will give you a brief about how hashing has been used in cryptography. In cryptography, basically you have two people called Bob and Alice. Bob is trying to send a message to Alice. Let's say Bob is trying to send hello Alice to Alice. Now this message has to be encrypted. This message has to be encrypted because if anyone apart from Bob or Alice gets hold of this message, it should be indecipherable. So this message is basically encrypted using a secret key, and once this message has been received from Bob, Alice can do the same thing. It can use the given secret key and decrypt the message into getting back "Hello, Alice." Uh, so hashing, uh, 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 the given string, you can apply a hash function to the given string, and it can give you an integer of given length, and you can perform some operations such as XORing or some more complex operations, combine using a secret key and the hash value of the message in order to produce this message. Now, since Alice can use the same secret key to uh, to 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 to, uh, to perform the same operation in reverse, and and get back the original message that Bob had sent. So now I have covered most of the topics that I wanted to cover. I've talked about, just as a recap, I've talked about a scenario where hashing has proved to greatly improve the performance. I've also talked about uh, how hashing has the most basic methods to implement hashing, and how collisions have been handled in hashing. I've also mentioned a couple of other applications of hashing, and I've also explained how hashing has been used in cryptography. Thank you.